So, excuse me. On Wednesday, you guys were supposed to watch a lecture that dealt with transient analysis of first circuits. So if you watch that lecture, um, you should have figured out that for a generic RL circuit, so I'm going to draw a picture of one here just really quickly. So for some generic RL circuit, let's call, actually, let's put the polarity the other way. This is VR. This will be VL. This is going to be our current IL. And this is going to be our current IR of T. So we found that all of these quantities will be of the form and y of 0 plus e to the minus REQ over LEQ. Sorry, that looks like LEG. T for T greater than or equal to 0 plus, excuse me. And then we also did a similar derivation for RC circuits. So if we have effectively the same circuit, but we replace our inductor with a capacitor, we're going to have a very similar response equation. Keep writing G's instead of Q's. So let's call this voltage VR. This is our current IR. This will be our voltage VC. And this will be our current IC. In this case, all of those signals, so every voltage and current in our system, will be of the form y of 0 minus for t less than 0 minus, and y of 0 plus e to the negative t divided by REQ times CEQ for t greater than or equal to 0 plus. So that was the results of our derivations that we did in Wednesday's lecture. Hopefully you all can see that these response equations are extraordinarily similar. In fact, they are the exact same thing, except that the coefficient that's being multiplied by time in the exponent is the only difference between the two things. So because these systems behave in such similar ways, electrical engineers have developed a quantity called a time constant that effectively allows us to quantify the rate of decay of an exponential function. And we don't really care if the system is an RC circuit or an RL circuit. We only care about the time constant. So our time constant, tau, quantifies the rate of exponential decay in a first order system. Okay. So for an RC circuit, tau is simply going to be R times C. And for an RL circuit, tau is defined to be L over R. So let's talk about why our time constant, or I guess these should be equivalent. And once again, I wrote a G instead of a Q. So let's talk about where these things came from. Okay. So if we look at a signal that is exponentially decaying, here is our signal of interest, y of t, and here is our time function. Like so. This value right here is y at 0. So we define a single time constant. So 1 tau to be the point at which our value here is y of 0 times e to the minus 1. Okay. And 2 time constants is similarly y to the 0 times e to the minus 2, and so forth and so forth. So what I'm going to do over here to the right is just make a little table here. Okay. So on the left-hand side is going to be time measured in time constants, and on the right-hand side is going to be the ratio of y of t divided by y of, let's be specific here and call it 0 plus. So at 0 time constants, our signal is at its maximum value. It's at effectively 100%. Okay. In 1 time constant, our signal has decayed to e to the minus 1, which is 36.788%. In 2 time constants, our signal is effectively at e to the minus 2, or 13.534% of its original value. In 3 time constants, we're going to have e to the minus 3, which is 4.979% of its original value. In 4 time constants, we have e to the minus 4, which is 1.832% of its original value. And the last one we're going to do is 5 time constants, where we're at 0.674%. So when we looked at these transient analysis derivations on Wednesday, we said that if I were to plot something here, let's say that this is our inductor current as a function of time, right? Let's do blue here. So we know that prior to our switch changing state or at DC steady state. Let me write this better. And then a long time after our switch closes, we are also at DC steady state. And then everywhere in the middle was our transient state. And we defined a long time as effectively what's happening at t is equal to infinity. So just a very long time after our switch has changed positions. Well, in engineering, we consider infinity to be 5 time constants. So effectively, 5 time constants is the amount of time it takes for a capacitor or an inductor to fully discharge all of its energy. Now, that's not technically true. It takes an infinite amount of time for it to fully discharge. But in 5 time constants, we see that the strength of the signal decays to less than 1% of its original value. And for engineers, that's good enough. So that's the concept of a time constant. And from this, we can now write a generic equation that is valid for either RL or RC circuits, which is this. Our quantity of interest could be resistor, current or voltage, capacitor, current or voltage, or inductor, current or voltage, will be Y of 0 minus for all t less than 0 minus, and it'll be Y of 0 plus times e to the minus t over tau for t greater than or equal to 0 plus. And we can apply literally the exact same equation for every situation that we deal with the understanding that we need to know how to calculate the time constant tau. Okay. So this concept of a time constant effectively ties the 2 different types of first order circuits together. So now we're going to talk about what's called the total response of one of these systems. So I don't remember if I used this term last quarter when I was making that video or not, but what we were dealing with before, which is this expression, is effectively what's called the natural response of the system. Okay. It's called the natural response of the system because it's what the system does when there aren't any excitation sources connected to it. So in all of the instances that we dealt with, our sources were disconnected from our energy storage element, right? So if we scroll up here, excuse me, our voltage source in each case is being disconnected from our inductor and capacitor. And so we are seeing how the system responds in the absence of some form of excitation. So what we're going to be talking about today is the total response, which is how it behaves when we include some form of excitation. So our total response Y total will simply be the sum of our natural response, which is what we've already talked about, plus what we're going to call our forced response. Okay. So we are going to look at this from the perspective of a capacitor circuit or an RC circuit And then we will infer from that how our RL circuits are going to behave. So let's look at a very simple and generic RC circuit where we have some voltage source connected through a switch to a simple network containing a resistance R in parallel with some capacitance C. And our quantity of interest in this case will simply be our capacitor voltage. And for this circuit, instead of opening up, our switch is going to be closing at t is equal to 0. Okay. So at t is equal to 0 minus, our circuit looks like this. Where at 0 minus, our circuit is at DC steady state. And so I'm replacing my capacitor with its DC steady state equivalent, which is an open circuit. So this is the voltage drop across our capacitor. Here is our resistor, and using our understanding of circuit analysis, excuse me, this should be minus. What should the voltage drop across our capacitor be? Zero. Absolutely right. So the voltage drop across our capacitor will be 0 volts because our capacitor is in parallel with our resistor, and our resistor doesn't have any current flowing through it. So if there's no current flowing through the resistor, there's no voltage drop over the resistor. And if there's no voltage drop over the resistor, there can't be a voltage drop over the capacitor for this circuit. All right. Let's look at T is equal to 0 plus. Actually, we don't even need to look at T is equal to 0 plus, right? So that's just going to be a waste of our time for this particular case. So let's just talk our way through it. So because the voltage drop across the capacitor cannot change abruptly, the voltage drop across our capacitor at T is equal to 0 plus has to be exactly the same as the voltage drop across our capacitor at T is equal to 0 minus. So if the voltage was 0 volts at 0 minus, it has to be 0 volts also at 0 plus. Okay. All right. So now let's look at what happens at t is equal to infinity. So in all of our previous examples, because we disconnected our source, effectively our signal decayed to 0 at t is equal to infinity because our capacitor or our inductor, whatever our energy storage element was, completely discharged all of its energy to the connected resistance, and that resistance turned that stored energy into heat. But now we have the opposite case where our source is going to be connected to our source is going to be connected to our energy storage element at t is equal to infinity. So at t is equal to infinity, our circuit is going to look like this. Our switch is now closed because our switch closed at t is equal to 0, and it's going to stay closed forever, effectively. We're still at, or I guess a better way to put this would be, we are again at DC steady state because we're at a long time after the switch has closed. And so if we were trying to figure out what our quantity VC at infinity is, what would the result be using circuit analysis here? So it won't be 0 again. So I'm trying to find the voltage drop across the capacitor. So let's call the negative polarity terminal my reference, and let's call this node up top VA, right? So the potential difference between node A and ground is VS. Everybody okay with that? I'm seeing nothing in chat and I'm hearing none of you talking, so I'm going to assume that you're on board with accepting that the nodal voltage VA is equal to VS. So our capacitor voltage is defined between that top node where VA is and that bottom node where ground is, right? So our capacitor voltage in this case must also simply be VS, which should be fairly obvious. If we connect a voltage source directly in parallel to a capacitor, then the capacitor has to have the same voltage as the voltage source. So if we were to plot this thing as a function of time, we're going to have something a little bit different, but very similar to what we saw with our natural response equations. So here's VC of t, here is t. Let's call this value, I'm going to use a different color here, Vs. So we're at 0 for a long time. So this is DC steady state. And then at t is equal to infinity, we're at DC steady state again. But in this case, our voltage is now Vs. And our transient condition is what's occurring in the middle. And what our equation is going to look like, or what our voltage is going to look like, is this. So it's going to slowly start to charge and then eventually settle to some final value. So this is our transient state here in the middle. And this is 0. So mathematically, this part right here, this DC steady state at the end, this is our forced response, okay? So this is what the forcing function is making the energy storage element do. It's making it have a voltage of Vs at t is equal to infinity because it's still connected to the circuit. So we are going to call this quantity simply y at infinity, okay? So earlier I said that the total response, y total, was simply the natural response plus the forced response. So I'm about to write something down here. There is going to be a small error in it, so we're going to talk our way through it in just a moment. So I wouldn't write things down just yet. We are going to have y at 0 minus for t less than 0 minus, and then y at 0 plus e to the minus t over tau plus y at infinity. So this is what generically our forced response is going to look like, or excuse me, our total response is going to look like. It's simply our natural response plus our forced response, where our forced response term is literally just what the circuit is doing at t is equal to infinity. Now, the problem here is that this isn't necessarily a continuous function, okay? So let me tell you what I mean by this. If we consider our little circuit that we had up above, what was y at 0 minus? So what was our capacitor voltage at 0 minus? Zero. All right. So we're going to have 0 volts where t is less than 0 minus. That's perfectly reasonable. Now let's talk about what our capacitor voltage was at 0 plus. So what was that? So at 0 plus, it wasn't Vs, it was still 0 because our capacitor voltage cannot change abruptly, right? So let's scroll up here and look at it. So at 0 plus, our voltage was still 0. So we are going to have 0 e to the minus t over tau, which this whole thing looks like 0, plus Vc at infinity, which was Vs for t greater than or equal to 0 plus. So effectively, our capacitor voltage looks like 0 for t less than 0, and it looks like Vs for t greater than or equal to 0 plus, based on this equation. So the problem here is that our capacitor voltage is not a continuous function. So let's talk about how we are going to fix this, okay? So the problem lies here with just using the value of 0 plus. So I'm going to modify this ever so slightly. And instead of saying it's just y at 0 plus, we're now going to say that it's the difference between 0 plus and infinity. Okay. So if we make that substitution, what we're going to have over here is 0 minus Vs e to the negative t over tau. So that at exactly t is equal to 0 plus, we have negative Vs plus Vs, which is equal to 0. And at 0 minus, we have 0, so we have a continuous function. Okay. So this guy right here is our new generic equation that we can apply to our first order circuits. Okay. Now, we can actually apply this equation to any first order circuit, even the ones that, like we worked on Wednesday, or I guess like you guys worked on Wednesday, because everything at t is equal to infinity for those natural response problems is just going to settle to 0. So if you can't understand what the difference is between a natural response problem and a total response problem, you can simply just apply this equation and you'll come out okay. So I would like to work an example problem demonstrating this. So the circuit that we are going to analyze is this guy here. We have a 3 amp source connected to an 8 ohm resistor. And then here we're going to have our switch. So this is going to be terminal B. This is terminal A. And then our switch is going to be closed at position A until T is equal to 0, at which point it closes at position B. Over here, we're going to have a 125 microfarad capacitor. Here we'll have a 7-volt source. Oh, and let me put a resistor down here. Here we have a 4 ohm resistor. Okay. So this is a total response problem because, well, really for 2 reasons. The 7-volt source never gets disconnected from our capacitor. So that's one thing that tells us it's a total response problem and not a natural response problem. Another thing that tells us that it's a natural or total response problem is that our current source is getting of 3 amps is getting switched into the circuit instead of being switched out of the circuit. Okay. All right, so we are going to very slightly modify the process by which we solve these things. Okay, so our first step will be to analyze our circuit at T is equal to 0 minus. And while we're at it, let's define what we're looking for. So let's say that we're trying to find the capacitor voltage as a function of time and this resistor voltage as a function of time. Okay. So at T is equal to 0 minus, our circuit is going to look like this. Okay, so here's our 3 amp source in parallel with our 8 ohm resistor. Terminal B is open circuited. Terminal A is where the switch is connected. So we are going to have our capacitor up here. Since we're at DC steady state, our capacitor is going to look like an open circuit. Down here is our 4 ohm resistor. And then we have this connection here. Our capacitor voltage is defined with this polarity, and our resistor voltage is defined, sorry, that should be minus, with this polarity. So how are we going to solve for VR at 0 minus and VC at 0 minus? And just throwing this out there, you're more than welcome to speak over Zoom instead of trying to type out some result. So VR is 24 volts. All right. So John, how did you get that result? Three times 8. So you applied Ohm's law effectively, right? So 3 amps times 8 ohms is equal to 24 volts. I don't have any problem with that whatsoever. There's literally nowhere else for that 3 amps of current to go. So that seems perfectly reasonable. What about VC at 0 minus? Anybody have any thoughts?
I got -7.
-7, I agree with that. So if we apply Kirchhoff's voltage law around this loop, so let's talk our way through this here real quick, okay? So we know that the current flowing through the 8 ohm resistor is 3 amps, and we know that the current flowing in this direction is 3 amps, which means there's no current branching off from our current source and flowing over to the right-hand portion of our circuit. We know that there's no current flowing up this way because it's an open circuit, which means there's no current flowing this way either. So that means the voltage drop across our 4-volt source, or excuse me, 4 ohm resistor, total brain part there, must be 0 volts. So if we do case VL around this right-hand loop, we're going to have VC plus 7 volts is equal to 0. And from that, VC must be equal to -7 volts. Does that seem reasonable to everybody? Any questions about the circuit analysis that was used? All right. So our next step is going to be to analyze our circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch has changed from being closed at position A to now being closed at position B. So that's going to cause some changes here, right? So our 3 amp source will still be connected directly in parallel to our 8 ohm resistor. But now we're going to have a short circuit up here. I'm going to leave this region right here blank. That's where our capacitor is going to be, and we'll figure out what to do with that in a moment. Here's our 7-volt source. And let me just double check things down here. Here is our 4 ohm resistor. And then here is terminal A, which is open circuit. So let's talk about what we're going to do with our capacitor. Okay, so I don't think I worked an example problem in the video that I recorded last quarter that dealt with a capacitor circuit. I may have mentioned it at the end of the lecture what we do, but we're going to talk about it here, right? So the voltage drop across the capacitor cannot change abruptly, which means that VC at 0 plus has to be the exact same thing it was at 0 minus, which is -7 volts. So at this specific instant in time, t is equal to 0 plus, we know that the voltage drop across our capacitor is -7 volts, regardless of the amount of current that's flowing through it. So this relationship describes an independent voltage source, right? Because an independent voltage source provides a fixed amount of voltage regardless of the amount of current that's flowing through it. So we're going to have a voltage source having the same polarity as our capacitor. So positive on the left, negative on the right, because that's how it was defined up above. And its magnitude is going to be -7 volts. This is the quantity VR at 0 plus we are trying to find. And just for the sake of argument, this is VC at 0 plus, which we know must be this value. Okay, so we don't need to solve for VC at 0 plus, because once we knew what it behaved like at t is equal to 0 minus, lets us plug that into our 0 plus relationship. All right, so what is our voltage VR at 0 plus? Anyone have any thoughts?
8 volts.
8 volts. How did you get that?
Well, with the -7 and 7 voltage sources cancel out, you have 8 and 4 in parallel. So just use current division.
Okay. So 2 amps is going to flow through the 4 ohm resistor. 1 amp is going to flow through the 8 ohm resistor. Okay, so 8 volts. That checks out. Anybody have a problem using current division like that? So effectively, what was suggested here is that we have the -7 volt source in series with a +7 volt source. So we can combine these two together. So effectively, it's 0 volts or a short circuit. That short circuit effectively puts the 4 ohm resistor in parallel with the 8 ohm resistor. So you could do current division to find the current only flowing through the 8 ohm resistor, or we could use Ohm's law, where our Ohm's law relationship is going to look like 3 amps times 8 times 4 over 8 plus 4. Yeah. So 3 times 8 times 4 over 8 plus 4 gives us 8 volts. So current division and then Ohm's law, or just use Ohm's law with the resistors in parallel. Anybody have any problems with or questions regarding the analysis that we did here in step 2? All right, I will take your silence as you all being okay with what we've done. So we're now going to have to do something a little new. We are going to analyze our circuit at t is equal to infinity. So at t is equal to infinity, our switch is in the same position it was at t is equal to 0 plus, but we are also at DC steady state, which means, excuse me, which means our capacitor in this case is going to look like an open circuit. So at t is equal to infinity, our circuit is going to look like this. So we have 3 amps in parallel with 8 ohms. Here is our capacitor voltage, VC at infinity. There's our 7 volt source. Here is our 4 ohm resistor. And then here is our terminal A. Okay. This is the voltage drop VR at infinity. And we need to figure out VR at infinity and VC at infinity. So anybody have any thoughts?
V of R at infinity is 24 volts, and then VC is -7.
So VR at infinity is 24 volts. I agree with, because that's simply 3 amps times 8 ohms is 24 volts, right? So any current that's leaving our 3 amp source, all of it has to flow through the 8 ohm resistor, because none of it can branch off and flow to the right through the open circuit that's representing our capacitor. So I'm okay with that, but I would argue that VC at infinity will not be -7. If we do Kirchhoff's voltage law around this loop, like so, we'll find out that it's going to be not -7. But to do that, we need to figure out what current is flowing through the 4 ohm resistor. It should be fairly obvious that since the 4 ohm resistor is in series with an open circuit, that current is 0. So we can say, since this current is 0 amps, this voltage is 0 volts. So from that, we have negative VR, so negative 24 volts plus VC at infinity plus 7 volts is equal to 0. Rearranging this, VC is equal to 24 volts minus 7 volts is 17 volts. Anybody have any issue with that? I'm taking your silence to mean you agree with me. All right, so we've determined our 2 quantities of interest at t is equal to infinity. So now we'll move along to our next step. Where we will determine our time constant for our circuit. Okay. So I'm going to put this here. It's really inferred, but I see students make a lot of mistakes. So during the transient condition, okay, technically our time constant only exists during the transient condition because we have no exponential decay when we're at DC steady state. Okay, so this is really implied, but because I see so many students make mistakes as to what circuit to use when they're trying to figure it out, I want to really spell it out for you. Okay. Excuse me. So there's only one capacitor in the entire circuit. So I would argue that CEQ here must be 125 microfarads, because it literally can't be anything else. So what we're going to do is we are going to look at our circuit during the transient condition from the perspective of that capacitor. Okay. So during the transient condition, I have my 3 amp source like so, in parallel with my 8 ohm resistor. Here's my capacitor terminal. So this is where we're looking in. Here is my 4 ohm resistor. Sorry, I jumped it a little bit ahead here. Here's my 7-volt source. We are trying to find a Thevenin equivalent resistance from the perspective of the capacitor. So because we're finding a Thevenin equivalent resistance, we need to be looking at a dead network, which means our 7-volt source needs to be turned off by shorting it out, and our 3-amp source needs to be turned off by open circuiting it. So what resistance do we see?
12.
12, just 4 in series with 8. All right. So from this, our time constant tau is just Req times Ceq. So that's 12 ohms times 125 microfarad. So 12 times 125 times 10 to the minus 6 is 1.5 milliseconds. And you'll see why I'm doing this in a moment. The inverse of tau is 2000 over 3 per seconds. Okay. So our last step here will be to plug stuff in to our generic equation. So our generic equation is as follows: y of 0 minus for t less than 0 minus, y of 0 plus minus y at infinity, all multiplied by e to the negative t over tau, plus y at infinity for t greater than or equal to 0 plus. So for our capacitor voltage, that's going to look like negative 7 volts here. And then we're going to have negative 7 volts minus y at infinity, which I believe we got to be positive 17 volts. Yep. E to the negative t over 1.5 milliseconds plus 17 volts for t greater than or equal to 0 plus. Doing a little bit of simplification here. That's going to be negative 7 volts for t less than 0 minus. Negative 7 minus 17 is negative 24 e to the minus t times the inverse of tau, so negative 2000 over 3 t plus 17 volts for t greater than or equal to 0 plus. For our resistor voltage, we're going to do something similar here. So our resistor voltage was 24 volts for t less than 0. And it was, excuse me, I think 8 volts. Yeah, positive 8 volts 8 volts minus 24 volts e to the negative 2000 over 3t plus 24 volts or t greater than or equal to 0 plus, where we can obviously say that this looks like negative 16 volts to simplify things. And there we go. So when we add sources into our circuits, it really doesn't change a whole heck of a lot about our analysis or anything that we're doing. We just need to remember that we have to analyze a circuit at t is equal to infinity now, because there's no guarantee that our quantities of interest are aren't zero. And we're modifying how we find REQ, CEQ, and LEQ. So effectively, we're modifying that fourth step to just say generically, find the time constant, where how we do that depends on whether we have an RL circuit or an RC circuit, if that's clear. All right, so do you guys want me to work another example problem, or do you guys want to work on the in-class assignment? What do you want to do? So John says ICA. Anybody opposed to doing the ICA? Do another example for funsies. All right, so let's do one with an inductor. So what I'm going to do here is, let's just find something. So I'm just going to find an old test. Let's see how much of a jerk I was being in spring of 2019. There's no exams in this folder, so not that one apparently. Winter of 2019. How are there no tests? Oh, I bet they're in Word, not in PDF form. Let me, something else. Winter 2019, exam 2. Yeah, here we go. All of them are in Word format. Let's look at exam form 21. And let's scroll way down to the end of the test and see what we've got here. All right. Give me just a moment to grab my mouse so that I can just copy and paste this circuit. Copy. All right. So this is going to be our circuit of interest that we're going to be dealing with. So it's pretty similar to the one we just worked, but it'll be different enough, I think, that we'll be okay. So we're trying to solve for our inductor current IL of T and our resistor current IR of T, where our resistor current is the current flowing through the 3 ohm resistor on the right hand side of the circuit. Okay. So at T is equal to 0 minus, what does this thing look like? Well, we have our 3 amp source. Connected in parallel to our 5 ohm resistor. Our switch is closed at position A. So effectively that means our 8-volt source here is just open circuited. It's not going to do anything, but I'm going to draw it for the sake of argument. And then over here, so since we're at DC steady state at T is equal to 0 minus, our inductor is going to look like a short circuit. And that short is going to be in parallel with the 10 ohm resistor. So I'm just going to not draw the 10 ohm resistor. And this is my current IL of 0 minus. And then here's my 3 ohm resistor. This is my current IR at 0 minus. And so we're going to figure out what IL of 0 minus is and IR of 0 minus by analyzing the circuit. So Hannah Riddick, since you were foolish enough to ask me to work the problem, I'm going to ask you to tell me what these two things are. Yep.
I genuinely do not know. I'm trying to follow along.
Okay, well then somebody else help Hannah out. Not trying to put you on Front Street or embarrass you or anything like that.
Well, IL is 0 is going to be 15 over 8. And then IR is 0 is the exact same.
I disagree with 15 over 8 pretty wholeheartedly. Oh, wait, actually, no, never mind. I definitely don't. Sorry, I was having a brain fart there. We're going to blame it on COVID brain fog. So yeah, we're going to use current division here. I was saying, oh, it's going to be 3 amps, but no, the 3 ohm resistor is in parallel with the 5 ohm resistor. So I'm blaming it on COVID. So let's see if the math checks out there. So using current division, we're going to have 3 amps times 1/3 over 1/5 plus 1/3. Yep, 15 over 8. And IR is the same thing as IL. It's both the current flowing through the both those currents are flowing through the 3 ohm resistor. So this is also going to be 15 over 8. So whoever it was that was talking a moment ago that said that's the correct answer, congratulations, you did it right faster than I did. All right, so from here, unless anybody has any questions about the analysis, let's go ahead and move to T is equal to 0 plus. So at T is equal to 0 plus, we are no longer at DC steady state. So our inductor is no longer a short circuit. And we also have to take into account that our switch is now closed at position B, right? So our circuit is going to look like this. So here's our 3 amp source in parallel with our 5 ohm resistor. Terminal A is going to be open circuited. Our 8-volt source is switched in like so. Here's our 10 ohm resistor. Here is our 3 ohm resistor. And then up here will be whatever our inductor is doing. So we know that our inductor is carrying a current of 15/8 of an amp directed from left to right. So I'm going to represent my inductor at t is equal to 0 plus specifically with a 15/8 of an amp current source like so. Here is IL at 0 plus, which we do not need to solve for because IL at 0 plus has to be IL at 0 minus because the current flowing through an inductor cannot change abruptly. And we are now trying to figure out what this current IR at 0 plus is. So, anybody have any thoughts about it?
Could you use source transformation to make it down to one voltage source and then find the current for IR like that?
So there are multiple different ways to do it. So that is absolutely one way a source transformation would work. We could do superposition.
Could you do current division to do this?
So if we did superposition, we could use current division. The reason why we can't use current division right from the jump is because our 3 ohm resistor appears in series with that 8-volt source. But using superposition, where we get to turn off that 8-volt source, makes it look like the 10 is directly in parallel with the 3. Let's do the source transformation because that was the first thing that was suggested, and maybe I was going to say maybe we'll check our work doing a different way, but I don't think that'll be really necessary. So one thing that I want to point out here, everything to the left of this red dashed line doesn't do anything, so I'm going to not draw it when I do the source transformation. Okay. So we have, just looking at everything to the right of the red dashed line, we have an 8-volt source, and then these are our terminals where we're going to put in our transformed thing. Here's our 3 ohm resistor, and then here is our current IR at 0 plus. Okay. So just for the sake of argument, I'm going to draw some terminals here so that it's very explicit what we are transforming and replacing with. So 15/8 of an amp current source in parallel with a 10 ohm resistor is going to look like 150/8 volts in series with a 10 ohm resistor. Is that correct? So let's start with this. So I'm saying that this should be 150/8 volts in series with 10 ohms. So did I do the source transformation, at least the math part of it, correct?
Yes.
Yeah, it's just 15/8 times 10. So I felt pretty strongly about that. So what polarity should the voltage source have? Positive polarity on the left or positive polarity on the right?
On the right.
Absolutely, because the positive polarity terminal should be on the same side as the head of the arrow. So positive polarity on the right because the head of the arrow was on the right. Now we have 8 in series with 150/8. So IR at 0 plus is going to look like 8 volts plus 150/8 volts divided by 10 ohms plus 3 ohms. Excuse me. So I got 107/52 amps. So a little bit over 2 amps. If we wanted to check that, let's see what chat's saying. Why is the 10 ohm resistor included in the circuit at t is equal to 0 plus, but not at t is equal to 0 minus? Okay, Cynthia, thank you for the question. So let's scroll up here really quickly. At t is equal to 0 minus, our circuit is at DC steady state, which means our inductor behaves like a short circuit. That short is in parallel with the 10 ohm resistor, which means effectively no current is going to flow through the 10 ohm resistor and there will be no voltage drop over the 10 ohm resistor. So it may as well not even be there. Another way that you could think about it would be, it's right here, it just doesn't do anything. No problem. All right, so let's settle back to here. So for those of you, because this source transformation, that wasn't, it wasn't obvious to me. It's absolutely a good suggestion because it allows us to just use simple Ohm's law relationship to figure things out. I would argue that mesh analysis would also be a pretty easy way to figure things here, right? Because if we have this mesh current, let's call that IA, that's obviously 15/8. And then we're only solving for this mesh current IB, where IB will be the exact same thing as IR at 0 plus. I firmly believe it will be the exact same thing as we find here. So we're not going to bother doing it, but that's just an alternative way that you could have used to solve for it. And like I said, as well, using superposition, you could have done current division to find the contribution of the 15/8 of an amp source, and then Ohm's law to find the contribution of the 8-volt source and added those results together. And it should also give you this same result. So 3 different ways, all fairly straightforward to determine that quantity IR at 0 plus. All right, so let's look at what's going on at t is equal to infinity now. I don't remember what this circuit looks like off the top of my head, so I'm just repasting it here so I can not screw this up. So at t is equal to infinity, we're gonna actually, yeah, that'll work. We're at DC steady state again. So our inductor is going to look like a short circuit, but our switch is closed at position B. So A is open circuited. And IL at infinity and IR at infinity will obviously have the same value here because they represent the same current. Using good old Ohm's law, this is going to be 8 volts over 3 amp. There's going to be 3 ohms is 8/3 of an amp. And the 10 ohm resistor is once again shorted out because our inductor looks like a short circuit at DC steady state. All right. So unless anybody has any questions about this, we can move along and determine our time constant. All right, nobody's saying anything. So our equivalent inductance is 150 millihenries because it can't be anything else. It's the only inductor in our circuit. So we're going to be looking at this circuit during the transient condition from the perspective of the inductor, right? So the inductor is up here. This is where we're looking in. Here is our 10 ohm resistor. Here is our 3 ohm resistor. Our switch is closed at position B so that our 8-volt source is in. 5 ohms over here. Three amps over here. And because we're finding a Thevenin equivalent resistance, we need to turn off our sources. So what do we see?
You get a REQ of 30 over 13.
Yes, a 10 in parallel with 3. Alrighty. So from here, our time constant is LEQ over REQ. So that is 150 millihenries divided by 30 over 13 ohms. Throwing that into my calculator. 13 over 200 seconds. The inverse of tau is then going to be 200 over 13 per second. And now we can plug stuff into our generic equation. So our inductor current, IL of t. So what was IL at 0 minus?
15 over 8.
All right. And then here we're going to have 15 over 8 minus IL at infinity, which was 8/3, I believe. Uh, 200 over 13t plus 8/3 of an amp for t is greater than or equal to 0 plus, and just for simplicity's sake, 15 over 8 minus 8 over 3. This bit right here looks like negative 19 over 24 amps. IR of t. So IR at 0 minus was also 15 over 8. And then at 0 plus, we had 107 over 52. Minus 8/3. And simplifying 107 over 52 minus 8 over 3. This is negative 95 over 156. All right. Any questions? Okay, so Monday's lecture usually isn't really a lecture at all. Okay. We've covered everything that we need to cover with regards to transient analysis of first order circuits. In fact, if you look at, let me pull up the homework assignment here. Oh, where the heck is my cursor? There we go. Get that out of the way. So if we look at the homework assignment number 15, This is literally the same type of things that you're already doing, except the circuits are literally just a little bit bigger. Like I would argue that homework set number 15 really helps you practice nodal and mesh analysis more than it does transient analysis, because you're just having to use nodal and or mesh to figure out what the quantities are at t is equal 0 minus, t is equal to 0 plus, and t is equal to infinity. The transient analysis part of it is the same as everything that we've been doing. Okay. And it's the same for these other circuits as well. They're just larger and more ugly because they have more nodes and more meshes. But the fundamentals of it literally do not change. So I don't usually actually lecture on the third day of transient analysis. I typically would have you guys work the in-class assignment problem, and then you would do a lab. So the problem with that is I still have to quarantine on Monday, so we can't do the lab because I'm not there to help you guys. So what I would like to use Monday's class meeting for is as a review session for our upcoming exam, which I do not remember what day it is. Let me pull up the syllabus. '30th. Okay, so that's a bit, the 23rd. So we're going to be reviewing a week early, but some review is better than no review, I would argue. We can either have a review session on Monday, or we can get ahead and start talking about op-amp circuits and then use the Friday of next week to do the review session. So which would you guys prefer? Op-amps on Monday or review on Monday? Get ahead. Anybody else? Okay, so all right, so we're going to talk about op-amps on Monday's class then. All righty, sounds good to me.